Hello, my name is Jawad Ahmed Fareed and I welcome you to our second session on pricing options using binomial trees. As I had mentioned earlier in our PowerPoint presentation, that we will build trees using two methods. The first method is the conventional method. It's the inefficient method of building binomial trees in Excel, and you'll see that it gets quite cumbersome and difficult very quickly. The second method is a more efficient method. I call it the Broadie method because I was the first time I came across this method and understood it was in a class run by one of my professors at Columbia Business School, who goes by the name of Mark Broadie. Broadie or Mark used to run a course, still does, called security pricing, which is where this technique was first developed and shared with its students. So the idea is we'll start off first with building a tree for pricing a basic option and then move on from that specific point in time. So if you see here on the top, I have a list of formulas. I have a formula for calculation of the probability P, a formula for the up movement, a formula for the down movement, and delta T, or the time step. So let's start with something very basic and simple. What do I need to calculate the value and price of an option? I need what I call a spot price, the value at which the option is trading right now. I need a strike price, the price at which I've agreed to purchase, buy or sell this option. Purchase, buy or sell the underlying. I need volatility or the underlying vol for the underlying security. I need a time to maturity. I need an estimate or a number for the risk-free rate, and I need the number of time steps. So time, or just call it steps, right? I'm assuming that in this specific case, the underlying security that we're working with does not pay a dividend and is a dividend-free stock. So if I were to take this step by step, let's say the spot price in this specific case is 100. Let's say the strike is also 100. Let's say the volatility is about 15%. Let's say time is 1 year. Let's say the risk-free rate is also 10%. And let's say we are looking at a single step tree or a one-step tree. So if you're doing a one-step tree, you're saying, if I were to start this is my starting price, spot price, and let's say this is my ending price, right? So I'll just highlight this so that we can look at this tree for our benefit, right? So we're saying I'm here, this is the starting point at time 0. Let's put in time here, time 0, and this is time 1. So I'm here at time 0, the underlying is worth 100. What would it be worth at the end of one specific point in time? So let's assume that we don't use the formulas that we've identified and highlighted here, and we just work off basic intuition. So basic intuition says that there is a 50% chance, so 0.5% chance, 50% chance of going up and a 0.5% chance of coming down. And let's also assume that in this specific case, let's say prices will go from 100 here to 115 here and to 85 here. Now, the option that we're looking at, let's say that we're pricing a call option, and this call option has the following parameters. It's the strike price for this call option is 100, which basically means that I have the right to buy the underlying for $100 at the end of 1 year. The underlying is right now trading at 100. I have the right to buy it for 100 1 year from now, and I need to find out what is this right worth. I have the right, not the obligation, but I just need to find out what is this right worth. So if I use this basis for calculation, what would be the payoff at maturity at this specific node? So the payoff at this specific node is going to be max of ST. What is ST? ST is the price at maturity for the specific security at this specific point in time, which in this case is 115. So ST minus X. X is the strike price that we've identified here. So we lock it so that we don't have to worry about copying and pasting incorrect cells later on, and comma 0. There you go. So this is the payoff profile. This is the payoff function that calculates and tells me what is the amount of cash that will change hand if the option expires at time 1 and the underlying is trading at 115. Okay. So the payoff by our calculation and estimation is about $15. Now if I apply the same rule here, I'll find out that the payoff is 0. And what I've just done is I've simply calculated the payoff function here. So if I want to estimate the value at this given specific point in time, I need to calculate a couple of things. I'm saying, look, there's a 50% chance that I'll get something which is worth 15 at the end of 1 year. There's a 50% chance that I'll get something which is worth 0 at the end of 1 year. What is the value of this right, this obligation, this option right now at this point in time? That is simply this probability times this payoff plus this probability times this payoff adjusted for the time value of money. So if I were to calculate time value of money using the specific parameters that we've identified here, the present value factor or PV factor is simply EXP minus R, the risk-free rate, which is this, times T, which is the time to maturity. Since this is a one-step tree, we're happy with using 1 as our estimate for delta T. There you go. So the PV factor is 0.904837. My estimate for the value of the option at this point in time is simply the PV factor, this number here, times the probability of an up move, which is this number here, times the payoff that I would realize if we actually end up in the up state, which is this number here, plus the probability of the down move, this number here, into the payoff if the down move is realized, which is this number here. There you go. Right. So what I'm basically saying is the value of this option at this point in time is simply the PV factor times the probability times the payoff plus the probability here times this payoff here. If I put this together, the value of the option that I get at this point in time is 6.786281. So this is intuition. This is common sense. We haven't used any of the formulas that we've highlighted here. We just plug these in. And what we want to see is if this is correct, if this is accurate, when we actually work with these calculations, how far off are we when it comes to actual results? So let's see that. So now if you were to go out and build a tree, we need to calculate a couple of additional elements. I'm just going to move this a little above so that we have space to add a few more rows. There you go. Alright, so what we've done is we've taken a first pass using simple bare bone intuition to find out what is an option worth based on a single step tree that allows us to look at two states, the underlying going to 115 up by 15% and the underlying going down to 85 down by 15%. We now want to calculate the value of the call option using a binomial tree, the same simple one-step binomial tree. However, we want to use the parameters that have been identified here. We want to see how much the numbers that we calculate here using this method are different from the numbers that we've just calculated. Right? So the first number that I want is what I call A, and A is simply the inverse of the PV factor that you see here, and I call it the accumulation factor. Right? So the accumulation factor A is our friend, this number here. All right. Oh, sorry, is 1 over this number. So it's 1 over this number here. And then I need to calculate U, which is the up move. And the up move, as you can see, the formula is right in front of us. The up move is simply EXP raised to the power volatility, which is sigma, into square root of time, which is 1 times step 1. Okay, so that's my up move. My down move is simply the inverse of this number, so it's 1 over the up move and I get my down move. My probability of an up move, P up, is A here minus D here divided by mu minus D here. There you go. Right? So that's my probability of an up move. My probability for down move is simply 1 minus P up. Right? So now I have two probabilities. I have probability of an up move as well as probability of a down move. And if I wanted to trace these, I can simply go to the formula tab, look at trace precedence, and ensure that the numbers that I've used are actually accurate. So I'm saying up move is, so the probability of an up move is simply A, which is ERT, E is power R minus T, minus D which is f8, and the whole thing divided by the difference between f7 and f8, which is the up move minus the down move, and that gives me p of up. 1 minus p of up gives me p of down. So now I have p, u, d, my delta t is 1. If I now need to look at this series, all I need to do is simply replace the probabilities, and not just the probabilities but also where do these numbers go from. So now we can simply build this tree, a shorter version of the same tree here, and what I will now do is I will say, okay, this is where I am, this is worth 100 and this is worth something. So okay, there you go. So create a little bit more space, insert, there you go, and I am interested in 1, 2 and 3. These are, sorry, 2, 3. Let's block them so that we can see them. There you go. That's my tree. Okay, so that's my tree. I'm saying you're worth 100 here. What's your up move? So at time 0 we have a value of spot of 100. At time 1 we need to find out how much would prices move. So we know that an up move here is the magnitude of a jump from one time step to the next, which means this 100 would simply be worth this value, which is 100 times the up move, and this is simply going to be 100 times the down move, which is here. There you go. So we're saying, it's not going to be 115 and 85, it's actually going to be 116 and 86. The probabilities are here, which are 0.811 for an up move and 0.1881 for a down move. Okay. And if I now use the same formula, I'm saying, what's my payoff? My payoff at maturity at time 1, if the underlying is worth 116, is simply max of ST, which is 116, minus X, which is the strike price here, comma 0. And I need to lock this in so that this gets copied without any problems. And if I were to, sorry, just this, not this. And if I were to copy this, there we go. So the payoff is this value and this value. The actual value of the option at time 0 using a one-step tree is then going to be the PV factor, which remains the same, does not change at all, after n.904837, into the probability of an up move, which is 0.81, into the payoff of an up move, which is this number, plus the probability for down move, which is 0.18817, into the payoff for a down move, which is 0. Calculate this, and the value of the option that we get is 11.8879, which is substantially higher and larger than the number that we see here. Right? So this was our intuitive estimate. This is our one-step model-based estimate. So the question that next comes up is, all right, if this is the difference, how do we know which value is right? Is this right? Is this right? Or something in between right? And we can only do that if we extend the number of time steps in the tree. So we go from, let's say, a one-step tree here to a two-step tree where we'll add one more layer of path, and we'll try and see how difficult or easy is it to build that two-step tree, and what kind of a difference or an improvement do we see in the accuracy of results, in the accuracy of our estimates. So if I were to now build a two-step tree, for a two-step tree things get to be a little interesting. So I'm going to skip the pieces that you've seen here and build a slightly simpler, easier to build tree, which simply means I go in this direction, there you go. That's my, so now this is my two-step tree, and I'm saying this is, if I use the same stencil, this is time 0, this is time 1, this is time 2. So I have two steps. I change the calculations and the numbers. Here I can simply change this, but this won't help because I have not defined or used these values. So I just simply introduced a piece called time step, and this time step is simply 1, which is the time to maturity, divided by the number of steps, and I increase the number of steps to 2 to give me half. So now my time step is half, and the time step that I see here represents 0, 0.5 and 1. And the initial starting point is the same, doesn't change. The initial starting point remains 100. This doesn't change. However, if I go up, I have to go and update a couple of elements here. So now before I update these elements, I want to make sure that I can track, that I can capture these values and these estimates. And what were these estimates? My first estimate, the first estimate, and my second estimate. My first estimate, which was this intuition based number, was 6.7862. My second number was 11.8879. And the reason why I've done this now is that as soon as I go and update any of these parameters in these figures, these numbers will change, which I would need to do, because if you remember, I'm now saying the PV factor is no longer going to be this number, it's actually going to be R into delta T, and delta T is our friend here, which is the time step. Okay, so that becomes my PV factor, which then has a direct impact on this factor, which is my accumulation factor, and then this is fine. The up move, there you go, there's up move. Now the delta T piece, this C9 needs to be replaced by, this needs to be replaced, this needs to be replaced by this, by the time step, which is half. So I plug this in and update this, and you can see that these numbers have changed again. So we now have an up move, down move, P up and P down, and you can see P up has now shifted from the 88% that we'd seen earlier to a slightly different number, which is 0.28522. And these numbers have also changed. However, it's only when we see the numbers, see the calculation, that's when we find out what the real actual impact is in our tree. So from 100, I go to 100 into the up move, which is 1.111, 4, and then from here we again go to let's just copy and paste here, which is 123. So we're saying go from 100 to 111 to 123, and similarly it'll come down from 100 to what's down move. Down move is our number here, 0.899, and just lock it so we can copy and paste. Control insert, shift insert. There you go. So we're saying, you know, this tree, this two-step tree, one step, two step, will go from 100 to 123 or to 80.88579. Now, the interesting element of these binomial trees is that these are called recombining trees, which basically means that if you look at this specific node, this node is actually two nodes. It's the downward move for this node, it comes down here. It's also the upward move for this node. So when you take 89.933 and you multiply this, let's bring our friends, the up move and the down move here. So our friend the up move is 1.111, and our friend down move is simply the inverse of that, which is number 8.899365. If I were to take this 89.936533 and I were to take and multiply this by the up move, so I'm going from here to here. If I do this, the number that I get, can you guess? The number that I get is most likely going to be 100. There you go. Right. Similarly, if I take this number 11.111.1895 and I multiply it by the down move, the number that I will get is also going to be 100. There you go. Right. So this is the property of binomial trees, especially trees that are used in option pricing, that we call that this is a recombining tree. This tree coming down, this branch coming down, and this branch going up will lead up or end up with the same value that you see at the branch below or the branch before, which is 100. Right. Okay, so now we've done this piece. Next question is, what is the option worth? We go to our friend max st minus x. St is 123.6311. Let's do F4 so that we can lock it. Minus x, and x in this case is strike, comma 0, bracket close. That's 23.6311. Control insert, copy and paste. So control insert, outside. Lock the wrong cell. It should be not, there you go. Need to lock in C7. So control insert, shift insert 0 and shift insert 0. Okay, so this row here is our payoff. And my next question is, well, if I'm standing at this point in time, and let's assume that the option that we're working with is a European option. It's an option that can only be exercised at maturity. So even though I may have something here, I cannot actually exercise it till I actually hit and reach maturity. If I'm standing at this point in time and this is a European option, what is it worth? It's worth the same amount that and we can reach that same amount using the same formula that we spoke about earlier, that we used earlier. It's worth the probability of this payoff times this payoff plus the probability of this payoff times this payoff discounted for one time step of interest or half a years of interest. And that's the answer that we'll get here. Similarly, this number is going to be this payoff into the respective probabilities discounted for one time step. And the value here is going to be this payoff, respective probabilities discounted for one time step of interest. Let's do this. So our PV factor is 0.951229. We take our PV factor, let's lock it, F4, and we say our PV factor into the probability of an up move. The probability of an up move is here 0.714 into the payoff of an up move, which is given here, plus the probability of a down move, which is given here, P down, into the payoff for a down move, which is given here. Alright, and bracket close, and there you go. So I'm saying, this is worth so probability of coming in a state where the underlying is worth 123 gives you a payoff of 23.63, plus the probability of coming into a state of 100 gives you a payoff of 0. These two combined, adjusted for interest, is worth 16.06659 at this point in time. What is it worth here at this stage? At this stage, it's worth the same process, same calculation. One step up, the PV factor into the probability of an up move. The probability of an up move is 0.714 into the payoff for an up move, which in this case is 0, plus the probability of a down move, which is 0.28525, into the payoff for a down move, which incidentally in this specific case is also 0. You close this, there you go. And then finally, the value of the option at this point in time is simply the PV factor that we've worked with so far into the probability of an up move here into the payoff for an up move. So then close this. There you go. Plus the probability of a down move into the payoff for a down move, which is here, bracket close, and the answer that I get is 10.92353. So you compare this answer with the numbers that we've calculated initially as part of our calculation. So our first estimate was 6.7862, our second was 11.88791, our third estimate using a two-step tree is 10.92353. And let's call this and label this as our third estimate. Right. So now what have we done? What we've done so far is that we've built a simple binomial tree. We built the first tree using our intuition. We built the second tree using the actual binomial tree model, but it was a one-step tree, so obviously there are and there will be going to be inaccuracies. We tried to improve the accuracy by going from one step to two steps, and then you can repeat this process till infinity. So going from two step to four step to 8 steps, and so on and so forth. The larger the tree, the more accurate the results, the higher the convergence, at least with respect to vanilla derivative contracts. Now the question, and I think the area that we need to focus on now is there a better and faster and easier way of building a tree? Because if I were to, let's say, build a 5-step tree, and remember this is a 2-step tree, if I were to build a 5-step tree, how would I start? A 5-step tree, there you go, so 1, 2, 3, 4, 5, and then similarly 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There you go. That's your 5-step tree. And the problem that you will face when you build this 5-step tree is, imagine the amount of trouble we went through in calculating these results and bringing them back and rolling them back in time. If I were to do this here, how many nodes would you need to do this calculation for? First, you need to do the calculation for payoff, which is here, which is the easy part, right? Because all it requires you to calculate the formula and calculate the results. Then I would need to repeat the calculation here, 1, here 2, 3, 4, and 5. Then I need to roll it back, 1, 2, 3, 4. Then roll it back again, 1, 2, 3. Then roll it back 1, 2, and then roll it back 1. Right? So there are multiple calculations, multiple cells, and as you increase the number of steps in the tree, you will find that the calculation piece gets quite intense and gets quite large. The question is there a better, faster, easier, cheaper way of doing this in the same fashion? Can I actually go out and build a 50-step tree in Excel without any problems and issues? And would you believe if I were to tell you that you can actually build, once you build a 5-step tree or a 1-step tree or even a 2-step tree using the Broadie method, the more efficient method, the method that we're just about to work on, once you build a simple tree, even a 5-step tree, extending that 5-step tree from 5 steps to, let's say, 100 steps will take you a few minutes. It took you more than just a few minutes to simply update and calculate this 2-step tree, this simple 2-step tree. You look at this 5-step tree and you can naturally say, I don't want to do this by hand. There has to be something there has to be something better than doing this by hand, and I'm saying yes, there is. That's exactly what we're going to do next. So in our next session, we'll take a look at the Broadie method, the more efficient method of building trees in Excel, and our hope is that by the time we're done with that, we will be very easily able to extend an Excel spreadsheet to calculate the value of an option for a European option as well as for an American option. And we'll do both calls and puts, and we'll see how easy is it for us to switch between calls and put as long as we have the right approach and the right method. So we'll stop here now. I hope this has been a useful session. I hope that the approach and the technique that we've used has allowed you to build a better appreciation for how the intuition behind binomial trees work and how it can be rolled out to higher level trees. Thank you very much for your time. This is Jawad Ahmed Fareed signing off for financetrainingcourses.com.